Hello. Can you guys hear me? Oh yeah, hi. Hello everyone. So today I'll be presenting mainly on the topic event streaming at scale and how at Myntra we built a fast, real-time and reliable ingestion pipeline with the help of Kafka and Delta Lake. So a little bit about myself. I am Shravan Varke. I'm an SDE at Myntra. I've been so for around 2.5 years or so. That has been my journey with Myntra. I work in Myntra data platforms. Within it, a subset team called NRT, which is responsible for providing real-time solutions to Myntra. So we provide solutions in terms of jobs and architectures to facilitate these real-time solutions. So today's topic is going to be on, is one of these solutions. And to set some context, let's talk about this. So in today's landscape, customers expect instant order placements and instant deliveries. This terminology refers to the real-time retail imperative, where target order deliveries are in the range of a few minutes. All companies are getting into this, and to address this, Myntra is stepping into this as well with the launch of MNow, where we are starting deliveries starting from 30 minutes or so. Now, as we step into this realm of quick commerce, it is very crucial for us to provide tools and systems that make this possible, that make this feasible, right? And that brings us to the need of why do we need this, right? So that brings us to the need for speed. Why do we need data in real time? Now, to meet these expectations of having data faster and quicker, it is important, we need systems that react in real time, provide predictions, provide personalized user experiences to everyone, and as well as minute-level inventory updates and a lot of other features as well. And it's crucial for us to provide key insights so that business teams can take actions at the right time. Any action that it needs to be taken at the right time is very crucial for us, right? And having these key insights is very important. And we essentially facilitate these particular things. One such example, as some of you guys might be aware about, is conversion rate optimization. So in an e-commerce platform, it is crucial to guide the user journey from the home page to landing page to the checkout. This essentially is called the user funnel. And essentially there are business teams which work on this to improve this funnel, the process of this funnel. So we deal with mainly conversion rate optimizations. So our goal was also to improve or reduce the lag or latency of this pipeline so that we can make these decisions faster, right? Now to achieve these things, to achieve this sort of, to achieve faster and quicker data, it was crucial for us to look at data differently. It was crucial for us to look change the way we look about this in a different way. So let's talk about what exactly is our architecture. So our architecture is mainly event-driven, where we essentially focus, where it's essentially a Lambda architecture. So Myntra, like many others, started with a standard dual-layered Lambda architecture approach, where we initially had a speed pipeline, which is a near real-time layer, which processed data in motion within a few seconds, and we had a batch pipeline, which processed data in a latency of a few hours or so. Now, this is the generic Lambda pipeline which everyone uses, but to satisfy our needs, this was a stopgap in that sense. Now, to address this is what our current architecture looks like, where essentially we have our ingestion layer, where data flows in, where the clickstream data flows in from Heimdall to our primary Kafka, and then it's routed to the near real-time layer, which works in a latency of around 30 seconds or so. And complementing it, we have our batch layer, which works in a lag of around 2 to 3 hours. Now, the batch layer works in bucketing fashion, which is why we have the lag of around 2 to 3 hours. And this was a key bottleneck for us. Now, looking deeply into this, what we can see is, if you look at the complete pipeline as a whole, now this was a complete batch pipeline which processed data from Kafka, landed it in Blob, and there was a batch job which essentially used to perform this aggregation and landed in Delta. The lag of this complete pipeline was in the range of around 2 to 3 hours. And this was a crucial bottleneck, and it was very important for us to reduce this SLA, reduce SLA of this pipeline. And our solution to this was stream ingestion. Now, with the help of stream ingestion, what we did essentially is we built a Spark. We upgraded the existing Spark job to convert it into a streaming fashion, where we directly consumed from Kafka, Confluent Kafka, while removing the intermediary hops in the middle, and landing the data directly in Delta. Now, this was crucial for us. This mainly relied on two key components. One is Kafka, and other is Delta, while Spark streaming facilitating the transfer of data from Kafka to Delta. Now, these two components played a pivotal role in this particular change, and I'll talk about why exactly. Now let's talk about some key considerations that came with this change. It was crucial for us to validate and make sure that this pipeline worked seamlessly. And there are a couple of challenges that come with transitioning a batch pipeline to a streaming one. One of those challenges is essentially ensuring data completeness. Now, data completeness is nothing but a data quality metric like you have any other data quality metrics, which talk about how fresh or how complete the data is. So basically, in a table or in a certain set of rows, how complete is our data, or how can we guarantee that our data is complete till a particular row? Now, this is a fundamental problem between batch and stream, where it's difficult to pinpoint in a stream, it's very difficult to pinpoint the exact location where the data is complete. It's a very difficult problem to solve. And it is a crucial one at that. Because when you have downstream batch and streaming consumers from this, it is very crucial for batch jobs to have a sign-off. So since batch jobs work in a bucket fashion, it is crucial for batch jobs to have a certain sign-off from the upstream pipeline so that they can proceed forward, so that they can proceed further. Well, if only when they have a certain sign-off from the upstream pipeline saying that, okay, my data is complete till 10:30, can I start processing the 10 to 10:30 bucket, right? And this sign-off is very important. Along with this, we also had to ensure that the data is accurate. Now, as you guys saw, we were looking at upgrading our batch pipeline. Now, our batch pipeline has to be consistent, has to be accurate. Now, because of this, we had to ensure that our pipeline is always accurate. There should be low risk of inaccuracy, and we should be able to mitigate any issues that come out of it. And to solve this, we essentially decided to take a step back and look at how do we consume data. So how does the Spark job? So if you guys remember before, we talked about, here essentially our Spark job consumes some Kafka and writes to Delta. Now to understand how exactly this works, let's take a step back and look at how this job consumes from Kafka. Now, this is a primary Kafka, and producing to this is our primary service, our clickstreams, one of our first touch points called Heimdall. This essentially produces data to our primary Kafka called clickstream Kafka, which contains almost over 1,000 partitions, and it produces this in a round-robin fashion. Now, this producing a round-robin fashion essentially pushes data to each of these partitions. Now, Kafka partitions inherently guarantee that your data that is being produced to each and every partition is sequential in nature. What exactly does that mean? It means that when a data lands in a particular partition, we can always guarantee that the data that comes, the offset that comes after is always sequential in terms of time. Obviously, there can be certain delays that can come because of producer level lag, but that lag would be in the range of a few milliseconds to a few seconds. To account for exactly this, we have a late arrival buffer, which essentially waits, or essentially is a buffer period, which factors in for approximately 5 minutes, and we give this buffer so that we can account or wait for the late arrival of events. Now, what happens is, now Spark essentially consumes from all these partitions in one go. So in each Spark micro batch, each task connects to each of these partitions, and it consumes data from all of these partitions. And how do we certify completeness or freshness to this? So what we essentially did is, we calculated the lowest timestamp in a certain micro batch, which was nothing but the freshness which is nothing but the minimum of all these timestamps, or the lowest timestamp in that micro batch, which then guaranteed that the earliest message in my group of partitions, or a permutation of messages, was always the lowest, and we accounted for a 5-minute buffer along with this. This guaranteed that any event, so the earliest event in this micro batch would be, say, 10:02, and this guaranteed that I would have no events older than 5 minutes buffer or so, because if I had a event that was afterwards, so if I had a 10:01 event over here, my minimum would be different and my freshness would be behind, and this allowed us to account for the late arrival of events. So if there was a late arrival of event within this 5-minute buffer window, the freshness would not proceed further, right? And this allowed us to essentially solve or mitigate the problem of ensuring data completeness, where we could propagate this, or we could essentially sign off on this freshness. So at 10:32 or so, I would have my data fresh. 10:35 or so, I would have my data fresh for 10:30, and then my batch job can start proceeding forward. Now, the other problem which I mentioned earlier was accuracy. To tackle this, I'll look back on one of the other components, Delta. So we are essentially writing our data to Delta. Now, to clarify a few things about Delta, so Delta is nothing but a file format, or in that sense, a metadata that sits on top of Parquet. Now, Delta inherently guarantees a lot of features. One of them being ACID properties, when you can perform ACID transactions on this data, on Delta, as well as you have data reliability and versioning. It also provides a couple of other features like time travel and a lot of other things. But the crucial important for us is asset properties. Now, because of this, when a Spark streaming job writes to Delta, the transaction that is committed by it is always atomic in nature. Because of this, what this allows us to do is that each micro batch that is processed is always transactional in nature, right? So this makes it so that the set of offsets that essentially are read are the same ones that are being written in that particular transaction. And coupled with Kafka's write-ahead logs, then provides us with a seamless or provides a clean consistency between read to write. Now, what exactly does this transaction mean? So the atomicity of this each transaction, where essentially a Spark job essentially reads or essentially pulls data from Kafka, commits these offsets to write-ahead logs, and then processes and writes this to Delta. Because of this uniformity in transaction, in case of any failures, this exact process would be retried from our write-ahead logs. And this guarantees us with a key special thing, so that we can have exactly one semantics. The way this works is, in case of any failures, the exact same microbatch would be retried, and we will have the same permutation of offsets, which are essentially committed earlier, being written to Delta. This guaranteed exactly one semantics and helped us solve the problem of accuracy. This can be integrated in Delta seamlessly with the help of adding transaction versions which correspond or are equal to our batch ID, and transaction app ID which indicates the job. Now, along with this, we had a couple of other things which this pipeline entailed was that we need to have scalability and reliability in that sense, right? Now, for scalability, essentially, our source side, we had Confluent Kafka, which inherently is quite elastic and makes it easy for us to scale, as well as it also ensures a high uptime and availability, so that it's easy for us to rely on Confluent for such a crucial pipeline. While our streaming job itself was hosted on Databricks, thus making it easier for us to scale up and down. Scalability is a crucial important factor for us, as during sales, we might have to scale our compute and everything else by a factor of 2 or 3 during special scale events. Along with this, we also have a backup backfill pipeline, which essentially processes data from a raw data pipeline, which and then writes to the same thing in case of data corruption. So this is a backup pipeline which is present just in case of data corruption or so. And because of this, we were then able to improve our lags, which were originally in the range of 2 to 3 minutes to 15 minutes, where we were able to land this data in a real-time fashion with 100% accuracy within 15 minutes. And yeah, this was an accomplishment. Thank you. That'll be all.